This is going to be the first problem from a series in which we're going to look at how to find the shear and bending moment diagrams for various beams and more specifically for various loading conditions. And this is the kind of problem that you might see as a first year or second year engineering student doing some kind of either aerospace or mechanical engineering. So if you'd like to see anything similar to this, or if you have any specific questions, let me know in the comments. So this should be a rather straightforward problem where we have a beam and then we have this uniformly distributed load which only occurs from the halfway point all the way to the right. So the first thing I would recommend doing, as usual, is just draw the free body diagram. So that's what I am going to do. So I'll draw the beam like this, and then we're going to draw and we're going to try to find the reaction forces. So in terms of reaction forces, we have three reaction forces, right? So we have this one, which is, I'm going to call it RAY. And then we also have RAX, because the support at point A can withstand both horizontal and vertical reaction forces, whereas at C we only have a roller. So at C we have this reaction force which we call RCY. Okay, and then in terms of the external loading, we have a uniformly distributed load which is called W, and then this is acting along the entire length of the beam, whose length is L, right? And the distance from here to here is just L over 2. So let's try to solve the problem and let's try to get to the point where we can actually plot the shear force and bending moment diagrams. And I will do this without using Macaulay's method. So this will be done without using Macaulay. So no Macaulay's method. I should have a few videos on the channel where I apply Macaulay's method, but this is going to be done in the standard way, which is going to take a bit more time, but should also be slightly more intuitive, as you will see. Okay, so let's first try to find the reaction forces. So the easiest one is RAX, which is just equal to 0. Right, so this is a statics problem, which means that the sum of forces in the x direction is equal to 0, and Rax is the only force in the x direction, therefore it's equal to 0. So let's do the same thing, but for the forces in the y direction. So I can write sum of forces in the y direction is equal to 0, therefore Ray plus RCy, so those are acting up, right? Because I'm considering my upwards direction to be positive, and then I have minus, so the green distributed load, that's minus WL over 2, and that's equal to 0. So we have one equation and two unknowns. So we have RAY and then plus RCY, and this is equal to WL over 2. So we still need one more thing to find the two reaction forces, and of course that's going to be done using balance of moments. So we're going to say that sum of moments about any point, so I'm going to write here any point, is going to be equal to 0, and I'm going to consider counterclockwise as my positive direction, because that's what I usually do, and that's usually what is considered to be standard. So you can take moments about any point. You can choose to take moments about a point that's not even in the plane of the diagram, but why would you do that? It's better to take moments about a point that's convenient. For example, I'll take moments about A. And the reason for that is if I take moments about point A, and this is point C, if I take moments about this point, one of the reaction forces is going to cancel. I could take moments about point C using the same logic, but I'll take moments about point A. If you want, you can choose to take moments about point C, and you'll see that you should get the same answer. So let's do this. I'm going to say sum of moments about A is going to be equal to 0, and of course counterclockwise is going to be positive. So about point A we have two moments. We have the moment due to RCY, which is counterclockwise. So we have RCY multiplied by the moment arm, which is L. Okay, and then we also have the moment, the clockwise moment this time, right? Because if you imagine that this point A is a hinge and the bar is actually a door, right? That green distributed load would rotate the door clockwise. So that would give us minus WL over 2. So that's the force, but now we have to find the moment arm. So this uniformly distributed load is actually acting at a halfway point, which is here. So that would be L over 2 plus half of L over 2, which is L over 4. So the moment arm is L over 2 plus L over 4, which is 3/4 of L, or 3 over 4L. And that's it. And that's equal to 0. So we can actually cancel out one of the L's. So we have RCY equals, and then we have 3 over 8 W times L. Right? And just for consistency, I'm going to write this as 1/2 WL, which means that the reaction force at A, so RAY, is going to equal half WL minus 3 over 8 WL, and this should be, let's see, we have 1 over 8 WL. And those are the two reaction forces. And we found out essentially that the reaction force at C is greater than the one at H, even 3 times greater. And it makes sense for it to be greater because the distributed load is skewed towards the right hand side of the beam. So it's actually acting all the way along the right half of the beam. Okay, so the reaction force at C is going to be higher, which is consistent with what we just found. So I'm actually going to drop the subscript Y because we don't actually have any X reaction forces. So I'm just going to call RAY as just RA. And this was 1 over 8 WL. And my RCY is going to be RC, which is just 3 over 8 WL. The first thing I would do at this point is to look at what happens on the left hand side. So I would split the beam in two, and the first part of the beam that I shall look at is the left hand side. And to do that, I will consider an arbitrary distance from the left hand side of the beam. So this is as usual, so this is point A. And I'm going to create sort of an imaginary cut somewhere, let's say here. And that length is going to be called X. And then we have a reaction force here, so we have an RA. And then we have a shear force here, and we also have a bending moment like this. So essentially, I took that imaginary cut on the left-hand side, and I replaced everything else with an internal shear force and an internal bending moment, and now we just have to find what those are. Also, the reason why I drew the shear force down and the bending moment counterclockwise on that right hand side of the beam is because that's what I consider to be the convention. So let's actually do that. Let's find the shear force. So we know that the sum of forces in the y direction has to be 0 because it's a statics problem. So we've got RA, and then minus S is equal to 0. So S, the shear force, is equal to RA, which is 1 over 8 WL. So in other words, for X between 0 and L over 2, the shear force is constant and is equal to the reaction force at A. So now let's actually do the bending moment too. So I'll do that here. I'll say that the sum of moments about point A is equal to 0. And again, counterclockwise is going to be positive. So if I take moments, and actually I think it might be better in this case to take moments about point P, where P is this cut. It's not necessary, but essentially you can do it. You can find the moments even if you haven't calculated the shear force yet. Because if you take moments about P, there is no moment due to the shear force, right? So let's do moments about point P. So I have, first of all, a clockwise moment about A, which is minus RA times X, right? Because about point P, this force creates a clockwise moment, and then I have plus M, which is my counterclockwise bending moment, and that's equal to 0. So M is equal to RA X, which is 1 over 8 WL times X. So you can see that the bending moment is not actually constant. It depends on X in a linear fashion, and we're going to plot this on the final shear force bending moment diagram. Okay, so I'm going to call this 1 because we did find the shear force and the bending moment, but that's only for the left-hand side of the beam, which is before that distributed load started occurring. So let's now look at, I'm gonna remove this. Let's look at somewhere here, right? So I'm gonna take another imaginary cut, but now that's gonna be somewhere on the right-hand side. So I'm gonna draw the beam like this. And point A is gonna be here. Point B is gonna be somewhere here. So now I have some distributed load occurring from point B going to the right. And of course, I'm going to stop where that imaginary cut was taken. And now my distance x is going to be this. So now my x is not going to be between 0 and L over 2. Now my x is going to be between L over 2. Actually, I can put equals here as well. So between L over 2 and L, like this. So let's see what we have. We have RA, we have the reaction at A, and then we have a shear force on this side. So sometimes you'll see the shear force being called V or Q or S in this case, and also a bending moment M. And this distributed load, we called it lowercase w. So let's first find the shear force. So we do sum of forces in the y direction is equal to 0, and upwards is my positive direction. So we have RA, and then minus W times, so now we have to find the distance along which W is acting. So we have that whole distance is X, we have this distance as L over 2, so that's going to be X minus L over 2, and then minus S is equal to 0. Right, so if we rearrange, we get that S is equal to RA minus W X minus L over 2. So S is going to be equal to RA, which was 1 over 8 WL minus W and then X minus L over 2. We can simplify things a bit. So the shear force is going to equal, so we've got 1 over 8 WL, and then you have plus 1/2 WL minus WX. Right, so we can add the two WLs. So we have 1 over 8 plus 1 over 2. That's going to be equal to 5 over 8 WL minus WX. So that's the shear force from point B onwards all the way to the right, all the way to point C. Okay, so let's do the same thing with the bending moment. So as before, I'm going to take moments about that point P. So we have sum of moments about P is going to be equal to 0. counterclockwise is positive, and let's see what we have. So RA, first of all, is producing a clockwise moment, so that's going to be minus RAX. And then we have that green distributed load, which is producing a counterclockwise moment, so we have plus. So the force is going to be equal to W times X minus L over 2, right? And the moment arm to P is from where this force is acting, which is like halfway. So that's X minus L over 2, everything divided by 2. And then we have M. So we have plus M equals 0. So if we rearrange, we have that M is going to be equal to RAX minus, and we can then write 1/2 M times X minus L over 2 squared. So we know what RA is, so that's 1 over 8 WL X minus 1/2 W, and then X minus L over 2 squared. And at this point, I would actually be tempted to just expand the brackets and also factorize 1/2 W. So we have 1/2 W, and then square brackets, we have 1 over 4 LX minus, and then I'll just keep this like this for now. So we have X minus L over 2 squared equals, and this is 1/2 W 1 over 4 LX minus, and then X squared minus LX plus L squared over 4, which should be 1 over 4, 1 over 2 W times, and then I think in the brackets we can combine a couple of times. So we have this, so we have 1 over 4 LX plus LX, so that's going to be 5 over 4 LX. And then we have minus X squared, and then we have minus L squared over 4. Which doesn't look like a nice expression, but we'll leave it like that. If you want, you can just say that M of X is going to be equal to 1/2 W, and then you can, write it like a quadratic. So minus X squared plus 5 over 4 LX minus L squared over 4, like that. So we have the functions of the shear force and the bending moment for the two halves of the beam. So now I'll start by drawing out the shear force diagram, which should be the easier of the two, as you'll see. So I have X, I have my shear force, and then I have L over 2 here, and then I have L all the way here. So in terms of the shear force, we know that for the left half of the beam, the shear force is just a constant. So it's 1 over 8 WL, which is going to be somewhere here. So it's 1 over 8 WL, and we're going to have this. Okay, and then for the other half, we know that the shear force is equal to this. So I'm going to write that out. Well, actually, we know it's equal to this, right? So I'm going to write it like that. So S is equal to 5 over 8. So 5 over 8 WL minus, and then we have WX. So it's a linear function in terms of X. And we know that it should start from that 1 over 8 WL. So let's check that. So if I say S calculated at L over 2, this is going to be 5 over 8 WL minus W times L over 2, right? Which is, if we multiply, we get 1 over 8 WL. So we get that the shear force at the halfway point is 1 over 8 WL, which we know that's true. Also, we should also get that the shear force at L, that should be equal to the reactive force at C, which is 3 over 8 WL. So let's check that. So S of L is going to be 5 over 8 WL minus WL. So that will be, if we amplify this way, this is going to be minus 3 over 8 WL, which makes sense. So the reaction force is actually this 3 over 8 WL, which is what we got. Okay, and the reason we have a minus, remember, is because we considered the positive shear force, the positive internal shear force, to be acting downwards, but we know the reactive force is acting upwards, which is why we have a minus. So this may not really be to scale, but we have minus, let's use yellow again, so minus 3 over 8 WL, so this happens here, and then we know this is a straight line, and that's what we have. So that's the shear force diagram. And then I'll do the same thing and plot the bending moment diagram too. So for the bending moment, let's use the whole page if we can. So we have X, we have M, the bending moment, and then we have L over 2, and we have L, like this. So the bending moment for the first half of the beam was not constant, but was just equal to this. So 1 over 8 WL times X, which is just a straight line, right? So we have a straight line starting from 0. So let's write it like this. So we have 1 over 8 WL times X, but this is only for X less than L over 2. So if we try to plot it, we're going to see that we will end up with 0 moment here. And the moment at the halfway point is going to be equal to, it should be 1 over 16 WL squared. Like this, and we just have a straight line. Okay, and then the other one, which is going to be slightly more complicated, is going to be the bending moment at, or the bending moment along the halfway, along the right half of the beam. So we've got that bending moment is going to equal this thing. So we have 1/2 times W times minus X squared, and then plus 5 over 4 LX, and then minus L squared over 4. Right, so we should get that M of L should be equal to 0 because we have simple supports on both sides, so we shouldn't actually end up with any moment at either end of the beam. So if we replace X with L, we have 1/2 W and then minus L squared plus 5 over 4 L times L, so again L squared minus L squared over 4. And you can see that this is 0 because minus L squared over 4 is minus 5 over 4 L squared, so this is 0, so this is 0. Also, the fact that this is minus x squared means that this is going to be a negative parabola, which means that we're going to end up with, I'm not going to bother to find the exact shape of it, but you're going to have something like this. Well, we'll try again. So we have a peak somewhere there, and actually the peak will correspond to this point, which I'm going to call this x star, and at x star we have 0 shear force, right? So we can try to do this in another video as to why this is the case, why maximum moment corresponds to 0 shear force, but essentially this is how this graph looks like. So this is the bending moment, diagram, this is the shear force diagram, and that's the end of the question.